Hi everyone. So I'm just responding back to your feedback from today. So these were some of the most common questions, or the questions I thought were most topically on point, or that I thought were of particular importance to people. Um, how can you identify when a system is at equilibrium? Actually, that's a really good question. It's not always obvious, both microscopically and macroscopically. So I'll just say for the time being, macroscopically, a system is at equilibrium if it's in a stable state and it's not changing and it's resistant to change. So case in point, I actually still have one of my supersaturated solutions. This system appears as though it's not changing, it's not occurring, no changes are occurring, but it's not resilient to change. If I try adding more sodium acetate to it, immediately it will undergo a very noticeable change when it all crashes out. So that system, even though it's not currently changing, it is not resilient to change. And that's another feature of equilibrium systems, is that if you have them at equilibrium and you try pulling them away from equilibrium, they'll actually naturally try to go back to equilibrium. That's a big idea. That's something called Le Chatelier's principle. And it's a key feature of equilibrium systems that they are always trying to attempt to go to equilibrium. So if you shift them away, they'll naturally try to shift back. Um, so that is one way that you can identify when a system is at equilibrium. But there's that. Um, how can a supersaturated solution go back to equilibrium? So actually, let me write that up here. So case in point today, when we crystallized the sodium acetate, we started with a supersaturated solution. So if the process that we were thinking about was taking a solid and converting it into aqueous. When we started with this supersaturated solution, we had too much of the solute in the aqueous phase. There was way too much in the aqueous phase, or the aqueous state. So it tries to shift backwards to equilibrium. If its concentration is too high, if it wants to shift back to equilibrium, its concentration needs to drop in some way. And the only way for its concentration to drop is for the solute to come out of the aqueous state and go back into the solid state, which is why the crystal forms. So yeah, its concentration drops and the system goes back towards the solute, so back towards the solid until it reaches equilibrium. And equilibrium, we said, is a dynamic process where technically at a microscopic scale, the particles are actually constantly shifting back and forth between solid and aqueous states. So even though, again, when I crystallize it and it looks like it's no longer changing, macroscopically it's not changing anymore. Microscopically, these crystals are constantly forming and deforming, a few atoms at a time. They're going out of solution, but they come back into solid. Sorry, they go out of solution, they go back into solution constantly. Let's see here. Which units are temperature dependent? So which of the concentration units are temperature dependent? So the concentration units that we discussed today, actually only one of them is temperature dependent, and that's molarity. So all of them are dealing with either moles, the amount of solute, and that's temperature independent. If I have a sample of copper and it's like 3 moles of copper in that sample, I heat it up by 5 degrees, I still have the same amount of copper atoms. They don't just disappear. So the amount of material is independent of temperature. I can heat things up and cool them down. That doesn't change. Same with the mass. You have conservation of mass. I heat it up, its mass doesn't change. I cool it down, its mass doesn't change. But volumes can change. Volumes are quite dependent on temperature. So for gases, you guys learned from the ideal gas law that when you were studying gases in Chem 110, that gases, if you heat them up, their volume expands. And that's essentially true for solids and liquids as well. They don't expand as much, but they do technically expand and contract a little bit with temperature. So I was discussing this with some people while people were working on the worksheet. If you've ever been in your house and you hear like the walls creaking in the middle of the night, that creaking is because the wood is expanding and contracting as the house goes throughout the day. In the nighttime, the wood contracts a little bit. In the daytime, it expands a little bit. And so when it expands, it rubs against and sort of squeaks against the other wood boards. So that's actually maybe not the best example, but that's for me the first one that comes to mind. Of the fact that substances, condensed phases, not just gases, will expand with temperature. So the point being that molarity is actually temperature dependent. The others, though, masses and moles, those are temperature independent. What's the difference between molality and molarity? When is molality useful? Well, for instance, I just mentioned one of the things that makes molality different from, and in some cases more useful than molarity, is the fact that molality is temperature independent. It is giving you a measure of the moles of the solute for a given amount of solution, but it's temperature independent. And that will actually be of importance when we talk about colligative properties, or the colligative properties are certain properties of solutions, like their boiling points, their melting points, and their vapor pressures and osmotic pressure. So those are properties of solutions that we're going to talk about in detail. But like, for instance, boiling point and freezing point of a solution changes as you change its concentration. So a dilute solution of salt water, if you add a little bit of salt to water, that tends to raise its boiling point. And the more salt you raise, the more the boiling point changes. The more the boiling point changes. So boiling point of salt water is dependent upon its concentration. But if it's constant, so you might want to come up with an equation that describes how does the boiling point change with concentration. That is something that we will work with. There is actually, I'll put it right to, I'll give it to you right now. There is an expression that shows you the change in the boiling point. It's proportional. I'll just say that it's proportional to concentration. But if your concentration is changing as you change the temperature, then that equation becomes considerably more challenging to express in any clean and neat way. So it'd be better if I could use a measure of concentration which is temperature independent. And that's one of the reasons why we introduce molality. Now, when we talk about colligative properties, those will frequently be expressed, the concentration of the solution will be expressed in terms of either molalities or mole fractions. So that's one thing that makes molality a little more useful than molarity in some cases. Other cases when it might be more useful is when you're making solutions, or when you're actually trying to make a solution. If you have a recipe, for a solution that says, so case in point, today I showed you guys a recipe for making a simple syrup. It called for a certain amount of sugar and a certain amount of water. Those are two of the components of the solution. Molality is kind of like that. It's the amount of one ingredient to the amount of another ingredient. So if I want to make a solution of a particular concentration, and I want to know how much of each ingredient do I need, it'd be more useful if I knew the concentration in terms of those two quantities. Molarity is different because it's not focused on the amount of either ingredient, or it depends not on simply on the amount of either ingredients. It depends upon the volume of the final product, the volume of your final solution that you generate. So that makes it a little bit more difficult to predict how much water do you actually need to make a certain volume of solution. So if you're trying to strategize how to make a solution, sometimes molality might be a better or more useful measurement. Um, Admittedly, those are situations that don't pop up that frequently. Molarity is much more commonly used, which is why you guys heard about molarity before molality. It is more useful. It's more useful for measuring out a certain amount of solute. So let's say I have a 5 molar solution. I have this solution. All right, let's see. Some particular reagent. So let's say I have an acid and it's a 5 molar acid and I need a certain amount of acidic protons for a chemical reaction. I have it in solution already. It's hard for me to measure out how many kilograms of solvent. It would make more sense if I had its volume. I can measure out volumes very, very easily. I can measure out the volume of a solution. Once the solution is prepared, it's easy to measure the volume. It's less easy to measure out how much mass of one of the components in that solution, because it's already mixed together. I can't separate them out and then measure the mass. The volume of the solution is the entire system. Everything's already mixed together and I can just deal with that one system. So that makes molarity more useful for measuring out solutions, which makes it good for stoichiometry type problems. Or any real world scenario where you have to worry about a proper amount of moles of one reagent. Molarity is your friend in that case. So when is each of the units useful? So I've already kind of given you guys a few ideas about when molarity is useful. Molarity is going to be useful in most of your laboratory settings, especially anytime you're doing chemical reactions. Molality is going to be good in when you need something to be temperature independent or you're trying to produce a solution. Let's see here. Mass percentages are when, yeah, they are both fractions. They both give you, so let's contrast mass percentage and mole fraction. They both give you some percent, express the amount of material in some type of a percentage. So they are both ratios. They are both unitless measurements. They are both fractions in some way. Mass percent, it might be you only care about what is the percent by mass in this mixture. So let's say you have a particular, let's say you're a metallurgist or you're in the Old West or something and you have a particular ore and you want to know what's its gold content. This particular ore that somebody turned in is 45% gold. I don't care about the moles of gold in it. I don't care about what's the ratio of gold atoms to silver and copper and silicate particles. I care about how much mass of gold I can get out of it. So I'm probably going to express the fraction of that ore that is gold in terms of a mass percentage. So that is one time when you care about the fraction, you care about one component versus everything else, and you actually care about macroscopic quantities. Mass is a fairly, for us, is a macroscopic quantity, something that we measure easily. So whenever you don't care about how many moles, the actual number of each particle, that's when it makes more sense to use mass percentage. So a lot of steel, a lot of alloys are given in terms of mass percentages. So there was an example in one of the last question on the worksheet. Steel, different variants of steel. Steel is a solid solution of iron and copper, and the different grades of steel differ in terms of their iron and carbon, not copper. So the different grades of steel vary in terms of their carbon content. And that carbon content is normally expressed as a mass percentage, because we prepare those different grades of steel by measuring out different masses of iron and carbon. When is mole fraction important? Mole fraction will be mostly useful to us in, I want to say, theoretical or hypothetical situations. Mole fraction is useful when you are taking a microscopic view of a chemical system, when you can actually see and count the number of atoms, or you care about the ratio of how many atoms of nitrogen, how many atoms of oxygen. So I'll give you an example of that is partial pressures. If you all recall from last semester, partial pressures are the pressures that a gas in a gaseous mixture exerts on the walls of the container. If you have a gas mixture, so it's not just one type of gas, it could be neon, helium, nitrogen gas, fluorine gas, hydrogen gas, all of them mixed together. Each one of those gases exerts a pressure on the container, on the walls of a container. And we learn that that pressure comes from individual collisions with those particles and the walls of the container. So you can relate the individual partial pressures to the total pressure based upon the mole fraction of each gas. And again, this is kind of a case where we're looking at it from a particulate, from a microscopic viewpoint. What fraction of the gas particles are oxygen? If 25% of the gas particles are oxygen, then 25% of the gas mixture's pressure is coming from the oxygen molecules. So whenever you're dealing with pressures and you're dealing with sort of like a particulate viewpoint, that's when mole fraction will be most useful for you. Now, if that question, I think I mentioned this in lecture, but I'll reiterate it. If the question is when is each of them useful, if you're talking about it in terms of, you know, if I have a problem and the problem asks me to calculate a concentration, which one should I do it in? It will be contextual. Each of these units of concentration is useful in different situations, different contexts. So the problem either will imply a context. It's an issue where I'll give you an example. I gave a problem today in that worksheet where you had a little cartoon of a gas mixture. In that case, the best way to describe the concentration is in terms of the mole fraction, because you can literally just count how many gas particles there are, and that gas particle, the number of particles is essentially a rate what's given by the moles of the particles. Moles is just a number of things. So that's one context where if I were going to say what's the concentration of argon atoms in that, it would be 1, because there was 1 argon atom over the total number of gas particles. So again, it's contextual, and sometimes that context won't be obvious, and I don't think I will ever give questions where it won't be obvious. Usually I will just tell you, calculate the molarity, calculate the molality. I'll be very explicit about which one you should calculate. All right, last question here. What's the difference between concentration and solubility? So solubility is a measure of concentration. So concentration just very generally is amount of one substance to ratio of the amount of one substance to everything else. Solubility is the maximum concentration of a particular solute in a solvent. So it's a more specialized, or it's a particular case where you're concerned about the concentration of one substance versus another. Solubilities are constant at a given temperature. Concentrations can vary. So case in point, I said that the solubility of sodium chloride and lithium chloride in water were 359 grams per liter and 800 and something or other grams per liter. Those values are constant at 25 degrees Celsius. So let me write that out here. So sodium chloride, 359 grams per liter. Lithium chloride was around 800 grams per liter. That's their maximum concentration. So that's their maximum. That's their solubility. but I could very easily make a solution of sodium chloride that was 200 grams per liter and another solution of lithium chloride that was also 200 grams per liter. So I could have two solutions that have the same solubility, I'm sorry, that have the same concentration, but the solubility of those solutes is inherently different. It's an inherent property of the solutes themselves. So it is, again, so it's specific to those substances. All right, so those were all the major questions, of the most common questions I saw on the feedback cards. Thank you again for all of your feedback. If I haven't answered your question specifically, please come and see me during office hours, or shoot me an email, or post it on the Piazza website. Anything, as long as you feel that your question is answered, that's important. Otherwise, I will see everybody on Wednesday. I hope you all enjoy your 3-day weekend. I'll see you later.